Today I'm going to talk about two new things. One is how to pipeline quantizer loops, so-called quantizer loop pipelining. And this is one approach where we can increase the speed of computing by reducing the iteration period bound. Anytime we have feedback loops, there is a fundamental lower bound called the iteration period bound, and we are challenged with improving the iteration bound for feedback computing systems. And one of those feedback computing systems is the decision feedback equalizer, and we'll get to that. But let me begin with a simple quantizer loops, that is a feedback loop containing a quantization operation, and there are numerous applications of those kinds of systems. And after that, so the basic idea that allows us to perform quantizer loop pipelining is the so-called parallel branch delayed decision. If we know that certain variable takes finite number of values, I can compute all of those values. I can update all of the future values in parallel and then delay the decision. That means select the correct one little bit later. So we'll talk about that, and then I will talk about, okay, sometimes the DFE, the decision feedback equalizer, cannot really be operated at high speed even after the quantizer loop pipelining approach. And then we need to use other approaches such as further pipelining and parallel processing. And so we'll talk a little about that, and the basic idea there is similar to the carry select modified tree adder paper that we talked about before, and really the recursive doubling idea with two feedback computations running in parallel. So we can call that double recursion look ahead. So we'll talk about that. So okay, let me begin with a simple quantizer loop. So let's say that I have a computation that says xn plus 1 is equal to the quantization of axn or alpha n xn plus un. Okay, so this is a kind of computation that is very, very common in a lot of applications in communication systems. So this is basically saying that I have a feedback system that starts with the output xn. Let's say this is xn. And then multiply that by a certain time varying coefficient alpha n, and add that to an input un, and then take that result and quantize that to a certain number of levels. So for example, I might be interested in quantizing them to two levels, -1 and +1. I may be interested in more levels. So this one delay is really what makes it a first order loop, first order quantizer loop. And if I had two delays in the loop, so that would be a second order loop. So we can talk briefly about that as well. So what do you think is the so-called iteration period bound? If I go around this loop, so the feedback loop has feedback computation time, so the iteration period bound to infinity is the multiplication time, that's that one, plus the addition time, plus let's call this quantization time. So that's the time to take the input and quantize them to two levels. So we can do a sign check. If it is greater than or equal to 0, let's say we can call it +1, otherwise we can call it -1. Divided by, that's the loop computation time divided by number of delays, which is 1. And usually that's a big number. So if you think about the critical path of 1 multiply, 1 add, and this quantization operation, that is going to be a substantial amount, and it will prohibit us from operating these kinds of loops at higher speed. Okay, so how can we speed up these quantizer loops in real applications, whether they may be applications of high-speed interconnect? So one application might be high-speed interconnect, where we are trying to connect two different points. Other applications, of course, would be in DFE, decision feedback equalizer. We'll talk about that some more, but that could be one application. There are other applications such as differential pulse code modulation, DPCM, or adaptive DPCM. So there are a lot of applications where we come across these kinds of loops, feedback loops containing a nonlinear operation such as a quantization operation. In communication systems, differential pulse code modulation, we might be interested in modulating the signal here. The signal takes two values, +1 or -1. Okay, so it turns out, I asked this hypothetical question when I hadn't thought about what are the real possible applications, and clearly a few years later people became very interested in gigabit Ethernet, and we'll talk a little about how these ideas that I had published in 1990 or 91 became quickly used in all the gigabit Ethernet products. Okay, we'll talk a little about that, but let's talk about what's the basic idea. The basic idea is very simple. So if this quantization part is taking the input here is taking two possible values, that means xn is not any arbitrary number. It can be +1 or -1. And if I know that it takes only two possible values, then what that tells me is this quantity can take two possible values. If xn is +1, this is going to be alpha n. I'm not writing the n, but alpha n plus un. And if xn is -1, well, that's going to be -1 times alpha n plus un. So what that suggests is I can take this system that seemed like a very slow system because it has a large critical path, and now because I can recognize that xn takes finite number of values and compute the possible next state values, xn plus 1 is the next state. And I don't know which one of these it is, but I do know that it's either this or that. And then as soon as I'm able to select one of these, that's the delayed decision. So this is called the parallel branch. So I'm computing two of these outputs in parallel, and I can delay the selection of these two. That's called the delayed decision. So I can take the decision a little later. Okay, so so essentially, I could compute alpha n plus un. So I compute alpha n plus un and minus alpha n plus un, and then I can also quantize these two. So I can quantize that quantization operation +1. Let's call this Q, that block Q. So that's a quantization operation that quantizes that result to +1 or -1. Okay, so I can quantize these as well. So now I have a binary variable here which is +1 or -1, and a binary variable here which is +1 or -1. And then I can decide which one is going to be the correct value by having a 2-to-1 multiplexer. So if I have a 2-to-1 multiplexer that selects either this or that, so let's say this is the current signal xn. Xn selects one of these two. So xn takes two possible values. It's either +1 or -1. So if it is +1, then the correct value would be quantization of alpha plus u. So if xn is +1, I select the top path. If xn is -1, then we select -alpha plus u, which is this part. By the way, don't worry about this +1, -1. You can think about if xn as a 0, 1, the binary variable, and then if it is 1, we can say if it is 1, it represents +1, 0 represents -1. We can interpret this is after all a two-level decision, which means it can be represented by a binary variable. Okay, so that's a very simple way, which is the basic premise is parallel branch, delayed decision. So we computed these two in parallel and we delayed the decision. Now, if you think about what is the iteration period bound of this computation. Well, the iteration period bound is simply, surprisingly, the time to perform a 2-to-1 multiplexer operation. So the new loop that we have has only one 2-to-1 multiplexer in that loop divided by one delay, and that's the iteration period bound, and that's a gigantic reduction from what we started with, which is the multiply time plus add time plus the quantization time. So now we are computing all of these multiply. So there is there is a dummy multiplication because the multiplication is not a real multiplication because xn is +1 or -1. So and then the add plus u and the quantize, these all have been removed outside the feedback loop. Everything has been removed. So the add operation, the quantization operation, we are performing these in parallel because there is one path for +1, one path for -1. Okay, so that's a very simple. That's the first paper that I was assigned to read, the July 91 transactions and circuits and systems paper. You don't really need to read a lot of that paper. I think if you read section 2, so just read section, section 1 is introduction, but just read one section, section 2. I think that might be, let's see, that might be enough, I suppose. It might be enough. I would have to, let me take a look and see if there is more in section 3 that might be of interest. I see. No, section 2 is fine. Section 2 is sufficient. Okay, just read section 2. No need to read beyond that. Okay, so let's think about how to extend this very simple idea to two possible applications. So first, what happens, so we can think about what happens if this quantization level is a 4-level quantizer. We can talk about a 4-level quantizer. And then we can spend some time talking about what happens if it is a second order. So I talked about the first order quantizer loop because there is only one delay. So what happens if it is a second order quantizer loop? So let's briefly talk about these two before we get to the point that the Mach's delay is still not sufficient. If I am trying to operate a serializer, deserializer, so-called SerDes at probably, maybe I'm able to operate something at 800 megahertz. The Mach's delay, let's say, is about a nanosecond, then I could, with 20% extra time for clock setup and hold and all those kinds of things, let's say 1.2 or 1.25 nanoseconds, then I could operate a equalizer at 800 megahertz. But what if I'm interested in operating an equalizer at 10 gigabit per second or 10 gigahertz equivalently, and we can't get 10 gigahertz clock because clocks are limited to about a gigahertz, and that means I need to go to parallel processing. So if I have a clock speed of 800 megahertz and I want a throughput of 10 gigabit per second, then we need to have a parallel equalizer where the level of parallelism would be 10,000 divided by 800, whatever that number is. So we'll talk about that. That's kind of our next. After I finish these two extensions, we'll talk about that part. Okay, so let me talk about if the quantize. The first extension is really not that difficult. So if I had 4-level quantizer, so I can say that. So we take the input and add whatever we'll see here, and then let's say I have a 4-level quantizer. Okay. Still first order. Okay, so let me use the notation in the book or the paper. So these quantization levels are assumed to be B1. So that's B1, B2, B3, B4. Okay, so those are the values. So that means the signal Xn takes 4 possible values, B1, B2, B3, B4, which means that I can pre-compute alpha n times B1 plus UN. So alpha n times B1 plus UN, alpha n times B2 plus UN, alpha n times B3 plus UN, and alpha n times B4 plus UN. I can pre-compute all of these, and not only that, I can also quantize all of these. Let me just write down them as Q, quantization blocks. And then finally, let's say that I have so these 4 possible values can be represented by 2 binary bits. So let's say that I have 2 binary bits, let's call these x1 and x2. And let's say that if x1, x2 are 0, 0, then that means this xn is b1. If this is 0, 1, 1, 0, 1, 1, let's call this b2, b3, b4. Okay, so then I have a 4 to 1 Machs. And then this is my, so by the way, this is a 2-bit control signal. This is a 2-bit control signal, which is x1, x2, and this is also a 2-bit control signal. And then I take that 2-bit control signal and feed back to the as control bit of the multiplexer. This is also 2-bit control signal. And if x1, x2, so if we call it x1, x2, and if these are 0, 0, that matches with b1. If this is 0, 1, that matches with b2, 1, 0, and 1, 1. So I have 2 bits acting as control signals to this 4 to 1 multiplexer. And then finally, the x1, x2 can be used to retrieve our final value, which is b1, b2, b3, b4. And that's not that hard, so I can say, okay, well, that's actually not that hard. So I can say, okay, x1, x2 is a control signal to another. Okay, let's use it here. It's a control signal to another 4 to 1 mux. Inputs are b1, b2, b3, b4. And if this 2-bit control signal is 0, 0, 0, 1, 1, 0, 1, 1, and that's my final xn. So we've accomplished quite a lot. So despite the fact that the quantizer is 4 level, I have pushed them out. I am computing all possible values, what would have been all possible values at this point. I'm computing all those 4 possible values. I'm also quantizing all of them in parallel. Okay, and then finally I use a 2-bit control signal to update. So the state update, this so-called state update, the state update equation xn plus 1, this was our xn plus 1. So xn plus 1, the equation is still the same. So the xn plus 1 is quantization of alpha times xn plus un. The equation is still the same. It just so happens that this q, instead of a 2-level quantizer, I have a 4-level quantizer, but the equation is still the same. Okay, so we are using 2 binary bits as control signal to update the loop. So that whole loop here has been replaced by simply a 4 to 1 multiplexer loop. And I can get the final value of xn by another multiplexer loop. So multiplexer here. So one thing that I should point out is that all of these add, so I didn't show you, but there is an adder going on, alpha n times. Okay, let's just draw for one part. So b1 multiplied by alpha n plus un, that's really what is coming here. So there is a multiplication here, okay, and an add here. And so there are 4 parallel multiplications and 4 parallel add operations, 4 parallel quantization operations. And all of these operations, including the multiply, add, quantize, are not part of a feedback loop, nor is this multiplexer. What that means is I can pipeline them at any level. I can pipeline these multiply adds at any level, or the quantizer any level that I need. So ultimately the iteration period bound is simply the T mux 4 to 1. Okay, so that's the 4 to 1 multiplexer loop. Okay, so now let me just talk about the second extension, which is what if this was a second order loop. Instead of having 1 delay, it had 2 delays. And then we will talk more about further parallel processing of these things. Okay, so let's try to go back to that first order quantizer loop, and instead of having 1 delay, I have 2 delays. So think about a second order IIR digital filter. That's kind of a system that we are talking about here. So let's just take the simple example of 2-level quantizer, and then there's a delay. So this is, I can call this xn, and then I can multiply this by alpha 1n, and then there's another delay. So that's what that makes it second order, and multiply that by alpha 2n, and add these two and that. Okay, so that's really a second order quantizer loop. Okay, so there is an inner loop, which is what we have seen before. There is also an outer loop. So I have assumed a two-level quantizer, which basically means that this output xn, well, I took the example as +1, -1. I can stick with that example or call this B1, B2. It probably doesn't matter very much. Well, let's just take these as B1, B2. Okay, so so this is xn, and so we can also assume that if xn is so now I can actually represent. So the moment it is B1, B2, I need to call this by a binary variable. Let's call that an. So if an is 0, that implies xn is B1. If an is 1, that implies xn is B2. Well, it doesn't matter, but let's take the higher value. Let's call this one 1 and this one 0. So B2 is a negative quantity, at least in the way I am drawing it. And it may not be, so it doesn't. So let's take this. So now I have a binary variable an, and there will be another binary variable corresponding to xn-1. So this is xn-1. And this is xn, and we are updating the next state xn plus 1. So xn plus 1 is equal to, xn plus 1 is here. Xn plus 1 is equal to quantization of alpha 1 n xn plus alpha 2 n xn minus 1. Plus un. Okay, so that's the loop, and if you look at the loop computation time, the computation time is 1 multiply 2 adds and 1 quantization. So that's also the iteration period bound, which is multiply time plus 2 add times plus quantization time. Okay, how can I use the idea of parallel branch delayed decision here? Really, we are interested in pre-computing all possible values at this point. How many possible values will be here? Well, the xn itself could be B1 or B2. That's two possible values. Xn minus 1 can be another two possible values. Could be B1 or B2. Therefore, together, xn and xn minus 1 combination can be 4 possible values. So if I want to compute all 4 possible values of this quantity, I can do that. So let's say that xn and xn minus 1. So this is B1, B2, B1, B2, and this is B1, B1, B2, B2. Okay. So then the quantity that goes inside the bracket, okay, so that quantity is going to be, so let me write down xn plus 1. Okay. So xn plus 1 is going to be quantization of xn is B1, xn minus 1 is B1, so that's alpha 1, let me just not write n for a minute, alpha 1 B1 plus alpha 2 B1 plus u, okay. And then for this case, that's going to be alpha 1 B1 plus alpha 2 B2, xn minus 1 is B2 plus u, and for this case, it's going to be alpha 1 B2 plus alpha 2 B1 plus u, and finally q of alpha 1 B2 plus alpha 2 B2 plus u. Okay. So if I had a 6th order quantizer loop, 6 delays and 6 loops, one innermost and the 6th loop will be the outer loop, then I would have 64 possible things to pre-compute in parallel. So in this example, so I can pre-compute all these things, alpha 1 B1 plus alpha 2 B1 plus u, alpha 1 B1 plus alpha 2 b1 plus u, alpha 1 b2 plus alpha 2 b1 plus u, and alpha 1 b2 plus alpha 2 b2 plus u. And then we quantize these, that's the operation happening in parallel. And finally, I have 4 possible values. And these 4 possible values are now known, so I can pre-compute. If I assume that, I should be so let's call this an plus 1, let's call this an, and let's call this an minus 1. So so I'm using the binary variable that I had introduced, which is an. So an is equal to 1 means b1, 0 means b2. So let's just take a look. So this really corresponds to an equal to 0 or 1. And then this will correspond to an minus 1 is 0 or 1. So now the next state, an plus 1, is what we are computing out of the 4 to 1 multiplexer loop. And then I delay that to get the binary variable an, and then delay that again to get an minus 1. And finally, these two are fed back, these 2 bits are fed back as control signals to this 4 to 1 multiplexer. So let's take a quick look. So the case when both of them, so let me just write them down here. an minus 1. So an means xn is b1. So this is 1, 1. an 1 means b1. an minus 1 means b1. 1, 0, 0, 1. b2 is 0, b2 is 0. So those are the control bits. And then, so b1, b1, so that's 1, 1. By the way, if you look at this has to be reversed. Well, I have drawn them in a way that this is an and this here is an minus 1. Read these from right to left. 1, 1, 0, 1, 1, 0, and 0, 0. Finally, so now that I know that I have these 2 bits, finally I can put these in the as control bits to another 4 to 1 multiplexer so that I can compute the real output. The real output is xn, which is here. It's it's here, yeah. So xn is b1 or b2. No, I guess I don't really need. I need only a 2 to 1 multiplexer loop because so this is fed back as control bit, and then I need only 2 to 1 mux. So if an is 1, I select b1. If an is 0, I select b2, and that is xn. And once again, these can be pre-computed. They are not part of any feedback loop. The quantization, multiply, add, these are all, we can pipeline a cut set here so that the critical path, well, this is out of a delay, so it's not really, I don't need to pipeline this anymore. So that's really how we can reduce the critical path by removing the quantizer out of the feedback loop by the parallel branch delay decision. So let's now go back and talk about what happens if that amount of speeding up the clock speed or sample speed is not sufficient. So now I'm interested in talking about what happens if we have a feedback loop that needs to be processed at much higher rates. Okay, so we are now interested in parallel processing of the multiplexer loop. So that's really what we are interested in talking about. So you can read the VLSI paper from 2005. So let's go back to that simple 2-to-1 multiplexer loop. So if I have the 2-to-1 multiplexer loop, let's call this AN, which is 1 or 0, and if it is 1, so let's call this. So there is something being pre-computed. We don't need to worry about these things. So there is something being pre-computed. Let's call this AN and BN. If AN is 1, I select cap AN. If AN is okay. So I should have a feedback. I should have a delay element, otherwise it will be non-computable. It will be non-computable. So let's call this as AN, and this is the delayed AN minus 1. So now, what we are really interested in is how do I increase the throughput of this simple multiplexer loop. And then we can go back and apply the same idea to the complex system. Okay, so this is a binary variable that takes 0 or 1 value. So I can say AN, the next Boolean state, AN is equal to AN minus 1 times AN plus AN minus 1 bar times BN. Okay, so that's the equation that describes the Boolean variable state update. Okay, so now one thing I didn't say, but it's assumed that if this is taking 2 values, this AN and BN are also Boolean variables or binary variables. So they also take values 0 or 1. So let's think about a very simple thought process. So let's say that this one can lead to a clock speed of 800 megahertz. Let's say that the clock speed of this critical path is 1.25 nanosecond as an example, and the clock speed is 800 megahertz. Now I am interested in a sample speed. As a simple example, let's take 1.6 gigahertz or 1600 megahertz. That suggests that I need a system where the level of parallelism is 2. 1600 megahertz divided by 800 megahertz. I need to have a 2 parallel computation. How can I obtain a 2 parallel computation? Well, in a 2 parallel computation, I need to think about, so in a sequential computation, we could update AN using AN minus 1. So let's think about a 2 parallel system. So I am now interested in computing a 2 parallel system, and let's say that we are computing something like let's call this a 2K and a 2K plus 1, and we are updating. So if this is 2K, remember from parallel FIR filtering, this is going to be a 2 slow operator. So these are the 2 parallel variables, that Boolean variables that we are updating, and this will be a 2K minus 2, 2K plus 2. So it might be better for me to just call this 2k and this 2k minus 2, and then call this, I could call this 2k minus 1. Okay, so so for now, at least for now, let's think about, I need an equation where I can compute a2k as some function of a2k minus 2. Okay, so what does that say? I need a so-called two-step look ahead, which means that I need, so before I apply n equal to 2k, I need an equation where I can compute an as a function of an minus 2. That's where the ideas from the multiplexer paper that I talked about comes into play. So I need to compute an using an minus 2. And not only that, I can also use a bar n minus 2, because after all, this is a multiplexer. So an is computed using 1 2 to 1 multiplexer using the an minus 1 as a control bit. And now I am interested in using an minus 2 as a control bit to compute an. So the way we do that, okay, so an is equal to an minus 1. So let's first talk about what is an minus 1. So if I just substitute n is equal to n minus 1, I can write down an minus 1 is equal to, just substitute n is n minus 1, an minus 2, an minus 1 plus a bar n minus 2 b n minus 1. Well, that's good news. I don't have any an minus 1 here. I've eliminated that. That's good news. Now substitute this an minus 1 here. Okay, if I do that, so write down wherever that is, this whole thing. So that is equal to an minus 2 an minus 1 plus a bar n minus 2 bn minus 1 times an. I am done with the first term. Now I have to go to the second term. Okay, so now, well, it was easy for me to substitute n by n minus 1. So replace n by n minus 1, and I can write this down. Now what I need now, I need to replace a bar n minus 1 by something in terms of n minus 2, that times bn. Okay, so, but how do I really get an equation where I can substitute n by n minus 1, and then this whole thing becomes a bar n minus 1. So this whole thing is a n minus 1. Now I need this whole thing to be a bar n minus 1. Okay, what that means is that I need an equation that expresses a bar n. And as you will see throughout, that's really the idea of, we are not just using look ahead to these recursive computations, but it's really at each and every step we are maintaining two-level recursion. So that means I need a separate equation. It is not given to me. Nobody told me what a bar n is, but I do know what it is. A bar n. So if this a n minus 1 was 1, if this was 1, let's call this was 1, then what's a n? A n is going to be cap a n. What's going to be a bar n? So if this is going to be a n, this is going to be a bar n. So I can write this as a n minus 1 times a n bar plus a bar n minus 1 b n bar. Okay. Now I have created a double recursive process. At each and every step of look ahead, we need to apply look ahead to these equations, these recursive equations at same time. So this is the very basis of what I can call double recursion look ahead. We are applying look ahead simultaneously to these two recursions. So every time I have an, I write down another recursive equation for a bar n. If this variable is 1, a is cap an, and then a bar is cap an bar. That's easy. If this a bar is 1, that means a is 0, then this a is bn and a bar is bn bar. I had already told you that these are Boolean variables. So if one of them is an, the other is going to be an bar and bn bar. Okay. So now in fact, I can substitute n by n minus 1 and write down this part here for a bar n minus 1. So a bar n minus 1 is going to be just replace n by n minus 1, a n minus 2, a n minus 1 bar plus a bar n minus 1, b n minus 1 bar. And that is the equation for an. So now I can manipulate them. I still want to express them as multiplexers only, in terms of multiplexers only. And so we can then say an is equal to, so let's write this down as something. So what I ultimately want to do, I want to write this down as an is an minus 2 times something, maybe call some cn or something, and dn. Okay, so that's what I want to compute. So take an minus 2, take out outside a bracket from these two terms. So that's an minus 2 taken outside a bracket. I have an minus 1 an, that times that, plus an minus 1 bar bn. Great, okay, that's good. And then I have a bar n minus 2, b n minus 1. Okay, I'm not writing something correctly. Okay, so this is a n minus, well, I am not writing something. First of all, this should be n minus 2, okay, and then, okay, let's just, so then a bar n minus 2 taken outside a bracket from these two terms. So we are left with b n minus 1 a n plus b n minus 1 bar b n. Okay. Okay, so that's, so how do I really draw this in terms of a circuit? So I look at these two terms and I see that this a n minus 1 is a control signal because that's here and here. And then b n minus 1 is a control signal. So I can have, so let's say this is a n, and I delay that to get a n minus 1. I have b n, I delay that to get b n minus 1. And then I have a n minus 1 is a control bit to a 2 to 1 multiplexer with inputs a n and b n. With inputs a n and b n. So that if a n minus 1 is 1, I select a n. If it is 0, I select b n. This is this bracket term. That's this bracket term. Let's call that cn. And let's call this whole thing dn. Okay, so this is cn. And then the next one, bn minus 1 is a control bit to a 2 to 1 multiplexer with inputs again a n and b n. So the same a n and Bn are input, and if Bn minus 1, this is Bn minus 1, is 1, I select a n, and if it is 0, I select Bn, and finally these two are fed to a 2-to-1 multiplexer loop that is computing a n from a n minus 2. This is a n minus 2 is a control bit. If a n minus 2 is 1, I select Cn. If it is 0, I select Dn. So that is how I can create two delays. I've created two delays in the feedback loop. So of course the iteration bound is now a multiplexer by a 2-to-1 multiplexer divided by 2. But I can't really fine-grain pipeline this multiplexer because I can't increase the clock speed beyond 800 megahertz. We can assume the 800 megahertz to be a communication bound. So then the goal is to really take this circuit and unfold by factor 2 to obtain a 2 parallel circuit, 2 parallel multiplexer. So we started with a 2-to-1 multiplexer loop, which is here. Now the intermediate process, if I want to create a 10 parallel loop, I need to create 10 delays in that feedback loop. Why is that? Because each delay, first of all, I need in the parallel system, I need minimum one delay for computability. And that one delay must correspond to 10 sample delays if a parallelism factor is 10. So I'm now taking a very simple case of L equal to 2 parallel system. So that means I need to create a multiplexer loop with 2 delays in the sequential system so that when I unfold that by factor 2, I have a 2 parallel multiplexer loop. Okay. So let's talk about how I can unfold this by factor 2. Okay, so let's start with a very simple. So we'll come back to the feed forward part. That's really always the easy part. We'll come back to that later on. But let's just take this multiplexer loop and unfold that by factor 2. So I have an. Okay, so let's call this node, simply call this A. Okay, let's call this node A. And these nodes are C and D. Okay, C and D. Okay, so I have A0, which is really A2K, and A1. So this is A1. Okay. And the two delays unfold that each now has a delay. Each has a delay. And then I need two multiplexers. So this is, let's call this C0, D0. C, node C is unfolded to C1, C0, C1. D is unfolded to D0, D1. And then that feedback, which was, well, I could call this node B. Okay. Then if this is A, this is B, after unfolding, this is A0, A1, A0 goes to B2, which is B0 with a delay, A1 goes to B3, which is B1 with a delay, and then B0 feeds to C0, D0, so that this is 1, 0. B1 feeds to C1, D1, so that this is 1, 0. And then I have, Oh, I have the delay already. Okay, that's then we are updating a 0. We are done with that. So that part is done. So that feedback loop is done. And then we need to take this these computations here. So this will be replaced by 2 muxes. This will be replaced by 2 muxes, and so on. So let's see how I can get to this part. So we are now, so let's say that I start with, let's see, we could call this node, so let's call this node A prime. Okay, let's call this node Bn minus 1 as B prime. So let's call these nodes A and B, and there are delayed versions A prime, B prime. Okay. Okay, so now I have so how do I compute C0? C0, okay, so let's see. C0 will be obtained by A prime 0. So this will be A prime 0 with inputs. This was AN and BN. So A0, B0. Okay. And then C1 will be computed using A prime 1 with inputs A1, B1. Okay. And then D0, this is node D, D0 has input control bit B prime and same input. So I could have same inputs, A0, B0. Well, we are running out of space, but so A0, B0, and the control bit is B prime 0, and then B prime 1, I think A1, B1, same as these two inputs. Okay. Okay, so we are done with those, and so I can mark this 1, 0. So last part is to really figure out. So we do have an input A0 and an input A1. So this we could call this A2K and A2K plus 1. So that's A0, A1. Bn, we have an input B2K and B2K plus 1. And this same A0 is fed here, same B0 is fed here, same A1 is fed here, and B1 is fed here. Okay. So now I need to get these control bits, the prime bits. So let's see. A delayed by 1 is A prime. So that means A0, so this is A0, goes to A prime 1. So A0 goes to A prime 1. So let me connect this here. A0 becomes the control bit A prime 1. Okay. A1 goes to A prime 2, which is A prime 0 with 1 delay. So A1, which is A2K plus 1, is delayed, and that becomes the control bit A0 prime. So A1 goes to A prime 2, which is same as A prime 0. Okay, now B prime is B with 1 delay. So B0 goes to B prime 1. So B0, which is really here and here, and that is, so this B1 is B0. Okay, so that's, and then B1 goes to B prime 2, which is B0 prime with 1 delay. So I take this signal, delay by 1, and that is the control bit B0. Okay, so that is the complete 2 parallel multiplexer loop. And we had to do a lot. Now I'm not really done, because remember, this is just the parallel processing of that loop. Now you have to go back and look at what was pre-computed. So there were a lot of things that had been pre-computed, and we need to put them back. And so if you look at what was the input to that 2-to-1 multiplexer loop, and that was things like this: alpha n plus un minus alpha n plus un and a quantizer. So I started by just assuming this to be an and bn, but what is an? So I need to compute an, and in this 2 parallel example, I need to compute a0 and b0. So, or well, I need to compute, if I call this an and bn, I need to compute a2k plus 1, b2k plus 1. So that means compute alpha 2k plus u2k quantize, alpha 2k plus 1 plus u2k plus 1 quantize. So we need to have 4 different things. So this a0, a1, b0, b1, there's a lot of pre-computation in parallel here that I didn't show, but that's part of unfolding that FIR part. So this is really the basic approach to parallelizing, and it really gets more and more complex. But the good news is a lot of the properties that I've talked about can be easily applied to finer grain pipelining cases or parallel processing cases. So if I want to have a 4 parallel, so let's say that I want a sample period of, in our example, 3.2 gigasamples per second. And clock speed is 800. So the parallelism will be 3.2 gigasamples per second by 0.8 giga, 800 megahertz. So that's going to be 4. How do I really get before I go to parallelism, I need to have a loop that has 4 delays in the feedback loop. That needs to have 4 delays. Otherwise, I can't apply L equal to 4. 4 delays in the word level processing become 1 delay in the parallel processing. Each delay in the parallel processing corresponds to 4 sample delays. So how do I get there? And the answer is really same as before. So if I call this Cn and Dn, so I go back to that equation there and say, okay, I know that An is equal to An minus 2 times Cn plus A bar n minus 2 times Dn. I know that. So now I have to constantly update double recursion. So this is double recursion look ahead because we are updating both A and A bar. So therefore I can simply write this as An minus 2 Cn bar plus A bar n minus 2 Dn bar. And then I start with An is equal to, now substitute, replace n by n minus 2, substitute here, replace n by n minus 2. So that's An minus 4 Cn minus 2 plus A bar n minus 4 Dn minus 2 times Cn times Cn plus A bar n minus 2, substitute n by n minus 2 here. Then we get A n minus 4 Cn minus 2 bar plus A bar n minus 4 dn minus 2 bar times dn. Okay. So now I can take these outside a bracket. So that's equal to a n minus 4 times cn minus 2 cn plus cn minus 2 bar dn plus a bar n minus 4 times dn minus 2 cn plus dn minus 2 bar dn. And surprisingly, the equation is very, very similar. I can write this as a n minus 4 times en plus a bar n minus 4 times fn. And to update the double recursion, I can say a bar n is equal to a n minus 4 en bar plus a bar n minus 4 fn bar. And then I keep going through that process. I can then repeat this process to have an L8 parallel if I go through that again. So the key thing here is, so now you will see that Cn minus 2 is a control bit to Cn dn, and here dn minus 2 is a control bit to Cn dn, and finally an minus 4 is a control bit to get an. All the properties that we have talked about apply very nicely, and then I can, after I get this feedback loop in terms of something with 4 delays, then I can apply unfolding to get a parallel processing system. Okay, so typically in a equalizer, this what I have described so far is really one first order equalizer, but typically in a real practical application, in a serializer, deserializer application, for example, we need a sixth order DFE, sixth order decision feedback equalizer. So how do I really extend the basic idea that, so okay, we should be thinking about the two possible extensions, which is the if the quantizer level was more than 2 levels, could have been 4 levels, and it could be second order, third order, whatever. So how do we compute the higher order multiplexer loop, and how do we parallelize that? Okay, so let me just see if I can write down the basic equation. So what's our starting point? In the in the first order case, my starting point was, say, a simple 2-to-1 multiplexer loop. Now what is my starting point for a 4-to-1 multiplexer loop? So there are two control bits. So essentially a so-called 4-to-1. So the starting point for a case like this would be so a 4-to-1 multiplexer loop can also be described by, so let's say this is A, N, B, N, C, and D, N, and then I take these, have a delay, and then take this delay, okay, so this is the starting point for a 4-to-1 mux loop. So I have some, let's call that AN, okay, AN, this is AN minus 1, and that's AN minus 2. So the two control bits are, I can call them 1, 0, 1, 0. So this is the whole thing here, this whole thing is a 4-to-1 mux loop. Okay, so now I have a 4-to-1 multiplexer loop that is described by these two loops. This is the inner loop and that's the outer loop. And both loops are critical. The loop bound is 1 multiplexer delay by 1. If you go through the outer loop, it's 1, 2. 2 multiplexer delays by 2 delays is still the outer loop is. Both are critical loops. Both are critical loops. Okay. So we are interested in computing AN So let me write down AN and let's call this EN and FN. So AN is equal to AN minus 1 times EN plus A bar N minus 1 times FN, where FN, EN, is AN minus 2 times AN plus A bar N minus 2 times BN, and Fn is equal to AN minus 2 times Cn plus A bar N minus 2 times Dn. Okay, so these three equations are the complete equations for the 4-to-1 multiplexer loop. So we have completed these equations. So how can I create, if I want to have two delays in the feedback loop that will allow me to get two parallel filter, how do I express AN using AN minus 2? Okay, and so that's really what we are interested in talking about. So if I want to change the number of delays from one delay in the inner loop to two delays in the inner loop, how do I express this in a way so that AN can be described in terms of AN minus 2? Okay, so, well, let's try to, so this can be a bit involved. It certainly could be a bit involved, and it is a bit involved, and does require patience. Okay, so I can write down AN is equal to is equal to A So let's first do this. So to describe this in terms of AN minus 2, so let's just write this as replace N by N minus 1. So I can write this as A replace N by N minus 1, E N minus 1 plus A bar N minus 1, F N minus 1. Okay, so then I can write this as AN minus 2 times EN minus 1 is going to be AN minus 3 AN minus 1 plus A bar N minus 3 Bn minus 1 times E n minus 1 plus, okay, we are done with En, let's see, An minus 2 times No, I guess I don't need this now, right? So an minus 2 times en minus 1, and this whole thing is en minus 1. Okay. Okay, so plus a bar n minus a bar n minus 2 times, yeah, I think this probably have to, let's see, we are running out of time, so I think I will stop here. Let me see if I can just very quickly maybe just show you the paper, and then I think it may be good for you to work on these things. Let's see. So let's see if I can quickly go through the paper that we are talking about. Okay, this paper is starting with an example of a second order feedback loop. That's why there is a 4-to-1 multiplexer. So this is figure 2 is describing a 64-to-1 multiplexer loop. So if you look at what we are showing here, think about this as a 6th order DFE, and this is a 4 parallel, and this is really the final circuit, I guess. 4 parallel 64-to-1 multiplexer. 64-to-1 multiplexer means there are 6 delays. 6 delays means 6th order decision feedback equalizer. That's why we have 64-to-1 multiplexer loop organized as these 6 stages of 2-to-1 multiplexer loops. So really, if you think about, there are so at the very last stage we have 4 muxes, and these are the 4 outputs, but we are not showing here for each F0 input there are 2 E0s. We are showing only 1 E, and similarly there will be, so there are 4 muxes here shown, but that's really 8. This is 16, this is 32, 64, and together, all together 128 A multiplexers. Each of these block is a multiplexer. I walked through the simple example where we talked about figure 2-to-1 multiplexer loop, and generate the 2 delays and apply the parallelism to that. So 4-to-1 multiplexer loop, that's what I was beginning to talk about. So these equations 5, 6, and 7 I wrote down, and so the goal is really how to get to figure 7. So that maybe you can go through a little derivation on your own to go through figure 7. So if you look at the nice property of that is still we have this 4-to-1 multiplexer loop exactly as it is, and all the pre-computation muxes are pushed out in the feed forward path. And then a lot of examples shown here. For 8-to-1, this is a 3rd order DFE, and again 8-to-1, there are 3 levels of multiplexers in the feedback loop with 2 delays in the inner loop and 1 delay in outside loops, and this whole thing here is outside the feedback loop, these multiplexers. And finally, if you look at this 3-stage pipelining of the 4-to-1 multiplexer loop. So this is 3 delays, so that would be 1 delay after parallel processing by factor 3. And because I have gone to 3 delays, I generate 2 columns of multiplexers, 2 columns, each feeding to each other. And this example shows an 8-to-1 multiplexer pipelining with 3 delays. So again we have 2 columns. If I want 4 delays, I need 3 columns. Okay. So there's a lot here. I think it's a good idea for you to at least derive figure 7. That might be a good idea. Okay, I will stop here. We will talk about stochastic logic next class.